I am back. So where were we? We were saying, what if we, we know that velocity, or the kind of the change in velocity, is acceleration times time. And I just wrote that a little bit more formally, really kind of incorporating the change in velocity, right? The final velocity is equal to the initial velocity plus acceleration times time. I actually could have written it like this. I could have written Vf minus Vi is equal to acceleration times time. And this is the change in velocity, right? And actually, that's the way I should be doing it. As you can tell, I kind of do some of this stuff on the fly. But I do that for a reason, because I want you to get the same intuition that I hopefully have, instead of just kind of doing it in a very formal way in a book. And sometimes the book doesn't necessarily make the connections in the most natural way. So this is going straight from my brain to this video, and hopefully into your brain. So these are all ways of saying the same thing. I actually should write this as change in velocity. The change in velocity. That triangle, or delta, just means change. So the final velocity minus the initial velocity is equal to acceleration times time. And the average velocity, we should just figure out, you take the final, you take the initial, and you average the two, is equal to this. And then I said, well, we know what the final velocity is. This is the final velocity. Right. The average velocity is this. We substituted for the final velocity, and then we came to this equation for average velocity. And then before I almost ran out of time, I said, I'm going to take this formula for the average velocity, and I really encourage you to just play around with these formulas yourself and derive it yourself, because it's going to pay huge rewards later on when you forget the formulas on your exam, but you can work it out anyway. So we have this formula for average velocity. Let's substitute it back into this. So we can say that distance is equal to the average velocity. Well, that's this. Vi plus AT over 2 times time. And if we just distribute that t, we have the initial velocity times time plus acceleration times time squared over 2. So distance is equal to the initial velocity. Let me draw a line here, not to confuse things. Distance is equal to the initial velocity times time plus acceleration times time squared divided by 2. And sometimes a physics teacher might just teach AT squared over 2. That's sometimes what people memorize. And that's because a lot of these projectile motion problems, your initial velocity is 0, especially when you're dropping a rock. So if your initial velocity is 0, this term would cancel out. And if you do that last problem that we just did, using this example, you'll get the same answer. Where, what did I say? I said, we're accelerating with gravity, so A is equal to 10 meters per second squared. And then time is equal to 2 seconds. And then initial velocity is equal to 0. So let me make some space here. So the distance is equal to the initial velocity 0, so this term just cancels out, plus acceleration 10 meters per second squared times time squared. So time squared, not actually that is. I was going to say not time square, time. Oh no, not time square, time squared. Maybe someone should create another square called time squared. But anyway, you have 10 meters per second squared. That was a bad pun. But times time squared. Time is 2 seconds. So it's 4. And since we squared the number, we should also square the units. So it's 4 seconds squared. All of that over 2. And like we learned before, well, 10 times 4 divided by 2 is 20. And then we have second squared in the denominator here, and we have second squared in the numerator here. They cancel out, and we're just left with meters. Actually, I'm going to leave it there for now, and then in the next presentation, I'll explore some of these mechanics even further. I'll see you soon.